Okay, good morning, everybody. Welcome for this new seminar on the Instituto de Astrofísica de Andalucía here in Granada. And today we will have the talk by Dr. Bahar Bidaran from the University of Granada in Spain. And she will talk about what stops star formation in isolated dwarf galaxies in the most undersent cosmic regions. So Dr. Bahar Bidaran, she's now a postdoc at the University of Granada, and she's part of the Cavity and Weave Aperitif collaborations. She got her PhD in 2021 from the University of Heidelberg in Germany. Previous to that, she finished her undergraduate studies in the Al-Sahara University in her hometown in Tehran in Iran. She's interested mainly in the formation and evolution of dwarf galaxies in different large-scale structures. So thank you, Bahar, for this presentation, and the floor is yours.
Thank you so much for the nice introduction and also for giving me the opportunity to present our results here today. Hello, everyone. Good morning. Today, I'm going to present you results of our very recent paper about star formation in dwarf galaxies in the most underdense regions of the cosmic belt, which are voids, filaments, and walls. So today, first, I will explain a little bit about, let me see. Yeah. So today I will explain a little bit about dwarf galaxies. What are they? What is their significance? Then I will explain you possible quenching mechanisms in these galaxies that thus far we know about dwarfs. Later on, I will present you the rare sample of quenched isolated dwarf galaxies in voids and filaments. And this will be followed by a discussion on what has possibly quenched a star formation in these galaxies. Okay. Dwarf galaxies, they are mainly characterized by their low stellar mass. So we usually call dwarf galaxies with a stellar mass, we usually call galaxies with a stellar masses less than 10 to the 9, 10 to the 9.5 as dwarfs, usually depending on the reference that you choose. They are also characterized by their low surface brightness, and that's what makes them a very expensive target for very deep observations. They are one of the most abundant type of galaxies in our universe, and in fact, recent results from Euclid also confirms that they are indeed one of the most abundant type of galaxies that we have in our universe. And they are important for astrophysics from different perspectives. For instance, they provide you extreme star-forming environments because they have low metallicity and low density. They are important entities for cosmological tensions, like too big to fail or the missing satellite problem, which is not really a problem now, considering the internal feedbacks. And also, more important than all, they are sensitive to both internal and external feedbacks, which makes them great testbed targets in order to understand evolution of galaxies. So we know galaxies are evolving and they are constantly affected by the internal and external feedbacks. And dwarf galaxies, because they are, first of all, the most abundant type of galaxies in our universe, so statistically, they are significant, and also they have a shallow potential, so it makes them super sensitive to both internal and external factors. They could hold the answer to key questions on the evolution of the galaxies. But we cannot really call all the galaxies with the stellar masses less than 10 to the 9.5 a dwarf. For example, here on the size mass, here I'm showing you, this is a plot that has been, that is built based on the figure 1 of Jans et al. So here you can see that in this stellar mass range of less than 10 to the 9.5, we also have compact ellipticals, which are not dwarfs. They are completely different beasts. So we cannot really consider them as dwarfs. Or in this stellar mass range, we have globular clusters, which are clearly not galaxies. And also dwarfs themselves are divided into different sub-branches that they are not, you cannot really consider them the same galaxy. So you really cannot consider an ultra-compact dwarf galaxy a similar case than a dwarf elliptical galaxy, or tidal dwarf galaxies, irregular dwarf galaxies. There are studies piling up evidence that they have been they have different origins, and that's why they are also going through different evolutionary tracks. So when we are talking about different properties of dwarf galaxies, like the gas phase metallicity, like the quenching mechanisms, we should really be careful that what a stellar mass range we are looking at and what type of galaxy we are looking at. So talking about quenching in dwarf galaxies, different mechanisms are believed to be responsible for quenching of a star formation in these galaxies, depending on their stellar mass. Starting from very low mass dwarf galaxies, 10 to the 4, 10 to the 5, in reionization epoch, most of them have lost their ability to form new stars. Reionization has killed many of these very small dwarfs, but our recent studies, particularly in the local group, confirms that most of those dwarfs that have been dead during their reionization, they kept dead for a long period of time, they kept quiet, and then recently they have started to form new generations of stars. How this happened, what is involved there is beyond the scope of this talk, but this is possible for a dwarf galaxy to not form stars and then start to form new stars, episodic star formation. It is something that we have seen, particularly in very low mass dwarf galaxies. Then from 10 to the 4 to 10 to the 8, we have supernova feedback. These galaxies are forming stars. Forming stars means also supernova feedback and stellar winds. These galaxies have shallow potential well, so it's super hard for them to retain the gas. So because of the supernova feedback, the interstellar medium can be heated, the shocks, the gas can be kicked out of the galaxy, and all of this can affect the star formation ability of the galaxy. We know mostly from theoretical work that up to the 10 to the 8 supernova feedback is an important mechanism for internally quenching dwarf galaxies. And there are very few observations confirming this, but for more massive dwarf galaxies between 10 to the 8 to 10 to the 9.5, according to the studies thus far, supernova feedback is not capable of completely quench these galaxies. For more massive dwarf galaxies, it has been only recently, and thanks to the high resolution observations that we have, that we now believe AGN feedbacks can be relevant. So we are now finding more traces of AGN in dwarf galaxies of the stellar masses 10 to the 9, 10 to the 9.5, and we believe that for some dwarf galaxies, AGN feedback can be also in charge of quenching them. So these are all internal feedbacks, but on top of that, we have the external feedback. And by external feedback, I mean environmental processes. So when a galaxy, any galaxy, not necessarily a dwarf, is inside a high-density environment, like a cluster, like a group, even as a satellite of a more massive galaxy, it is constantly under the effect of environmental processes. They are beautifully illustrated by Irie Chang in this illustration here. And as you can see, different phenomena. For example, we have ram pressure stripping in charge of creating these beautiful jellyfish galaxies. And this is basically the act of removing gas from the galaxy. And a galaxy that has lost the gas has lost the ability to form new stars. We have tidal interactions with different galaxies inside the group or cluster, or with the potential well of the cluster itself. That can also affect properties of the galaxies. It can affect the morphology, it can affect the star formation activity. Also, we have the mergers, we have the starvation. So these are acting on all the galaxies that are in a high density environment. But again, dwarfs are having shallow potential well, so they are explicitly sensitive to these environmental processes. And we believe that environment is the main killer of the star formation inside these dwarfs. Why? Because many of the physical properties of dwarf galaxies are showing correlation with the present-day environment of these galaxies. For example, the morphology density relation. What is it telling us? We have observed that inside a cluster, inside a group, even in our own local group, when you are in a high density part of the environment, like in the core of the cluster, in the central part of the group, the dwarf population is dominated by old dwarfs with red photometric color, low to no star formation activity, and mostly early type morphologies. Whereas when you go to the outer skirts of the cluster, outer skirt of the group, you are become more dominated by bluer galaxies with late type morphologies, and also the star formation rate increases. This has also been backed up by multiple statistical studies, like the one I'm showing you here by Galaxy et al. In 2021. So here you are looking at around 11,000 SDSS galaxies. What they did was that they quantified the host halo of all these galaxies, and then they binned them according to the size of the host halo. So here in pink, for example, you are looking at the galaxies of different stellar masses in a host halo as massive as 10 to the 14, which is similar to the Virgo cluster nearby. And they show that for low mass galaxies, here they are covering up to 10 to the 9.5, but other studies show that this trend also goes even lower to the lower stellar masses. You are looking at the fraction of quenched galaxies in different environments, and you are looking, basically their results are telling us that in a very massive host halo, like a galaxy cluster, like Virgo, the fraction of quenched galaxies is much higher. And when a host halo is massive, it means that it's more strong or it's more effective in influencing its satellites. It's more effective in tidal interactions, more effective in ram pressure stripping. And that's because in more massive galaxy clusters, we are seeing a much larger population of quenched galaxies, particularly dwarf galaxies. This trend also continues if you go to the individual cases, individual galaxies. This is what has Romero Gomez done in 2024. So they went to the Fornax cluster. Forget about the yellow and the red lines here. They are massive galaxies. Let's concentrate on the blue and green. So here we are looking at dwarf galaxies inside the Fornax cluster at different cluster-centered distances. So here in dark blue, we are looking at galaxies that they are in the core part of the Fornax, and in green, they are those that they are in the outer skirts of the Fornax. So they observed these galaxies with the SAMI IFU data. They derived the star formation history, and based on that, they could derive the cumulative fraction of a stellar mass that has been formed as a function of look-back time. So this plot basically tells you that what fraction of the present-day stellar mass in a galaxy has been formed at what look-back time, or at what epoch. And what they showed is that those galaxies that they are in the central part of the Fornax have basically stopped forming new stars, or has stopped putting more stellar mass to their present-day budget around 4 to 6 gigayears ago. And they have attributed that to the environmental effects, that because they are in the center of the Fornax, they have been there for more than 5 gigayears inside the cluster's environments. And that's how the Fornax has killed the ability of forming new stars in these galaxies. If you compare these profiles to those in the outer skirts of the cluster, then you can see that they are still actively forming the stars, because basically like this green line has formed more than 80% of this present stellar mass 1 gigayear ago. Like they are still active in forming the stars. Okay. So all of this information from the literature brings us to one main conclusion, that environment is the main actor in killing a star formation in dwarf galaxies. And this brings a hypothesis that if it's true, if environment is the main killer of the star formation in these galaxies, then we should not be able to find any isolated and quenched dwarf galaxies. And to evaluate this hypothesis, we went to the least dense regions of the cosmic web, to the void filaments and walls, using the cavity parent sample. Very briefly to introduce what is cavity. So cavity is a survey, it's an international collaboration, IAA is part of it. So the main goal of this survey is to characterizing galaxies in voids, in nearby voids. In 15 voids, we are trying to map all the galaxies with the IFU data, but also we have ancillary data for these galaxies. The first data release took place last summer. And also we are publishing more about the properties of galaxies in the voids. These are some of our very recent publications for those of you who are interested. But what I'm particularly interested are dwarf galaxies in voids. So let's go back to the dwarfs. How we selected this sample. This is important because I want you to also understand the limitations that we had. So we started from 42 voids that has been selected by the cavity collaboration. How they have been selected is basically they started from the Pan Catalog 2012. This is around 1,055 nearby voids. what they did is that they started to put several cuts and several criteria, but the most important ones for us to understand the discussion and the sample here is the cut on the redshift. So we are now only looking at galaxies within the redshift of 0.005 to 0.05. Also, only voids that has at least 20 galaxies are included in this sample, and voids on the edges of SDSS, like these parts and these parts, are removed because we wanted to be able to map the entire world and the galaxy in its entire world to be mapped. More details about the sample selection and several cuts are outlined in Perez et al. 2024, but the key point here is that there are several cuts here, and we are starting from 42 nearby voids. So the sample of 42 nearby voids contains 8,690 galaxies. As I told you, I'm interested in less dense regions of the cosmic web. So then let's also include filaments and walls. For that, we went to the sample by Dominguez Gomez. So this is a sample of 15,000 galaxies. Both of these samples are defining the same redshift range, and both of them are based on the SDSS. So both of them are affected by the limitations of SDSS in the same way. I'm interested in dwarfs. So the first cut would be on the stellar mass. I'm looking at galaxies with the stellar masses less than 10 to the 9.5. This is how the numbers are changing with different criteria. You can track them. I'm interested in quenched galaxies, so galaxies that they are not forming any stars. So the first cut would be the red sequence condition from Salas et al. The most important point here is that the numbers that we're going to end up at the end is the lower limit. Why? First of all, if you remember, we are not looking at all the voids. And second, because both of these data are from SDSS, and basically SDSS is not sensitive for very low surface brightness galaxies. So systematically, we are not including galaxies less massive than 10 to the 8.9. So the final sample that in a bit I will explain you how we ended up is not representing the actual population of isolated and quenched dwarf galaxies. It's just a lower limit for that. Then also this means that we are going to work on this part of the stellar mass range. And this is the part that environment is known as the main driver of quenching star formation in these galaxies. And also AGM feedbacks could be relevant as we have observed them in some of the galaxies using high resolution data. Okay, going back to the sample selection, we wanted these galaxies to be completely isolated because if you are a dwarf galaxy in a void, it doesn't mean that you are isolated. It means that you are in a less dense region of the cosmic web, but still you can be part of a galaxy group. You can still be a satellite of a more massive galaxy. So we wanted these galaxies to be completely isolated, so minimizing the effect of environment as far as we can. That's why we went to the Argudo Fernandez, and we put the same criteria for isolation. What is this? It means that we only selected galaxies that they do not have any neighbors within 1 megaparsec search area around them, relative velocity difference of 500 kilometers per second, and any neighbor brighter than absolute R-band magnitude of -17. This is the cut that we put for the isolation, and you can see how drastically the number decreases. So it means that you can be inside the void, but it doesn't necessarily imply that you are isolated. And the same also applies for the filaments. Clusters are not included because by definition, a galaxy inside a cluster is not an isolated galaxy. And also we didn't want these galaxies to have any traces of recent star formation activity. Also, we didn't want them to be AGN dominated for the same reason that I just showed you. That's why we went to the Sid Fernandez, and we put this criteria of equivalence width of H alpha less than 3 angstrom. This effectively removed the galaxies that had traces of star formation in the past few megayears, and also it removes the AGN galaxies coming from the Venn diagram. Here I'm showing you in gray all the galaxies from these two big catalogs. Then the dashed black line is the red sequence condition from Salas et al. In green, I'm showing you the isolated galaxies, and in black, I'm showing you the final sample, which there is still one step to reaching there, and that is to make sure they are completely quenched. So we went to the spectrum. The only data that we have for these galaxies is the SDSS, unfortunately. SDSS is a fiber spectrum, so it's a spectrum coming from a 3 arcsecond diameter fiber. This fiber is covering the spatial range of 0.3 to 1.6 kiloparsec within the redshift range of interest. And just for a comparison, a typical dwarf galaxy has a size of 1 to 10 kiloparsec. So for some of these galaxies, we are looking at the very central part of the galaxy, and for the other, we are looking at fairly the central part. So what we did is that we took the data from SDSS, the spectra. We discarded galaxies with the signal to noise of less than 12, because below that number, we saw that our fits are not really reasonable. Then we did the full spectral fitting using PyPipe 3D. I will explain in a bit that what does the full spectral fitting routine does. We did the fit between 400 to 700 nanometer using Niels stellar library and Vazdecki's single stellar population models. So here you are looking at the observed spectra in the dark blue. What does the full spectral fitting do is that it has a library of stellar population models for which we know the age, metallicity, chemical enrichment in terms of alpha over Fe. The code starts to combine this together so that they best represent the observed data in orange. You can see it here. Then it returns you a report, which means that what fraction of what SSP model I have used to produce this result for you. From that report, you can measure the average age, the metallicity, and also you can measure that what fraction of light inside this galaxy, this blue profile, has been formed at what look-back time. And with the mass-to-light ratio conversion, you can convert it to see what fraction of mass has been formed at what look-back time. And that is how that cumulative mass fraction function has been built. So based on that, also star formation histories can be investigated and quantified in different ways. One way is that we measure the quenching time of the galaxy, and that has different definitions. We are using the one that has been used widely in the literature, so also we can compare with the other studies, and that is the moment when a galaxy accumulates more than 90% of its present-day stellar mass, tau 90. And this is quenching time for galaxies that they don't have any traces of recent star formation or any gas reservoir, gas in their spectra, and that is the case for our galaxies. Okay, so this was the final cut, the signal to noise of the spectra and making sure that they are quenched. We ended up with 14 isolated and absolutely sure quenched dwarf galaxies in voids and 3 in filaments, but this is not this is not a total population of these galaxies, as I told you. This is just the lower limit. Okay, let's have a look at these galaxies. On the right-hand panel, forget about these thick lines, just look at the profiles in the background. So for each of these 17 galaxies, we did the full spectral fitting technique on the SDSS. Then we did 50 Monte Carlo. So the profiles that I'm showing you is the average of those 50 Monte Carlo, because one single fit doesn't give you necessarily the good answer. You should do it through iterations. The answers may change. So here there's the time, the tau 90, so the time that the galaxy has formed more than 90% of its present-day stellar mass. We have the tau 50. You can see that all of these galaxies have tau 90 more than 2 gigayears ago. Some of them even 7.9 gigayears ago, some of them more recently around 2.2 gigayears ago. So we believe that this difference in the tau 90 means that maybe they have been quenched through different ways, or different mechanisms are in charge of quenching them, resulting in different tau 90. Also, for the sake of discussion, just to continue the discussion in a better way, we decided to group these two galaxies into two groups of short time-scale star formation and long time-scale star formation history. You can do it in different ways. You can do it based on the KS test and the tau 90, so you can see two distinct distributions there. You can do it based on the difference between tau 50 and 14 gigayears ago, or the difference between tau 90 and tau 50. There are different ways to do it. To be consistent with also the literature that we are comparing with, we continued with the approach proposed by Dominguez Gomez, and that is dividing galaxies into two groups based on the fraction of a stellar mass that has been formed 12.5 gigayears ago, so 1.5 gigayears after the Big Bang, basically. Galaxies that have formed more than 20% of their mass by that time means that they have been formed their stellar population or their stellar mass in a very short time. We call them short time scale star formation historic galaxies, and the rest are called as long time scale, or those that have formed in a more extended. They have formed their stellar mass over a more extended time. That's the whole point of this work, is not to talk about this short time scale, long time scale, or the criteria that we chose. This is just to guide the discussion, and in a minute you will see why we needed this classification. But let's make sure that we are looking at dwarf galaxies. So if you remember in the beginning, I showed you this size versus stellar mass plot, and I told you that in this stellar mass range, you may look at different types of galaxies. To make sure that we are looking at dwarf ellipticals or dwarfs, typical dwarfs, we put our galaxies, these are the pink and purple data points, on the size versus mass, and we compared with the massive ellipticals and, more importantly, compact ellipticals. Because in the literature, there are several papers regarding finding quenched and isolated dwarf galaxies, but then they are turned out to be a compact ellipticals. Compact ellipticals are different than dwarfs. They are basically ellipticals that they are very compact. They have a very small size, and they are different beasts to understand what's happening there. On the background, we have in brown, we have dwarf ellipticals coming from Virgo cluster. So this comparison shows that what we are looking at are similar to the elliptical galaxies that we have inside the clusters that we see around us. And these galaxies are indeed dwarf galaxies. Okay, let's continue the comparison. So here, the thick or the solid lines are the average profile of the galaxies in the background based on this classification. So in the purple, we have the galaxies that the average profile of galaxies with short time scale star formation histories in voids and filaments, and in pink we have those that have long time scale star formation history. The same has been applied to the galaxies here in the central and the outer skirts of the cluster. Remember Romero-Gomez that I showed you, this cumulative mass fraction function in the Fornax? These are the same profiles. So the galaxies that are in the central part of the Fornax are in light green, and those in the outer skirts of the Fornax are in dark green. This is interesting because if you compare the pink and the light green, it means that you are looking at two populations of dwarf galaxies. They show similar star formation history, similar size, similar mass, but in completely different environments. One group is in the core of Fornax cluster, a high density environment, and the other one is inside the voids and filaments, complete isolation. Then this gets more interesting if you look at these two, the pink and the dark green one. Those galaxies that are in the voids and filaments, complete isolation, and have extended star formation history, still have much older tau 90 compared to the galaxies that they are in the outer skirts of the cluster today. And by outer skirts of cluster, I mean 0.8 to 1 virial radius of the cluster. So they are inside the cluster, they are affected by the cluster. Yet they are still forming stars, whereas we have a population of dwarf galaxies in complete isolation, and they have been quenched much time ago. So what are we seeing here? Is environment not playing a role, or are we looking at different types of galaxies? We know they are dwarfs. Maybe they have different origins. Let's see. We went to the individual galaxies, we checked them, and we found nuclear star cluster in the center of all the 17 galaxies that we had. What is a nuclear star cluster? Nuclear star cluster is a very dense and massive stellar assembly, usually in the center of the galaxies with the 10 to the 8 or 10 to 10 to the 10 solar masses. Our own Milky Way has a nuclear star cluster. So they have an effective radius of 4.4 parsec, which means that they are contributing between 10 to 50% of the total light we have observed with the SDSS. And in the stellar mass range that we are looking at, so between 10 to the 9 to 10 to the 9.5, the nuclear star clusters are believed to be formed as a consequence of in situ star formation. How are we sure they have a nuclear star cluster? We did a quick test. We went to the R-band images from the decal survey. We downloaded the images. We did a very simple elliptical model on the galaxies. We did the subtraction, and we saw that in all the galaxies that we have in our sample, there is a bright core in the center, and even 3 of them have some substructures like a disky substructure inside them. Okay, this gets more interesting. If we go back to this plot, and here this time, we go to the outer skirts of the cluster and only select dwarf galaxies that they are NSC host. So they have a nuclear star cluster in their center. We derive the star formation history, we do the averaging. It will be the black profile that I'm showing you here. So forget about the pink and purple. Let's consider only the outer skirts of the cluster. Galaxies that they do not have a nuclear star cluster tend to be more star forming or tend to have recent star formation quenching compared to those that they host a central nuclear star cluster. So is the nuclear star cluster the key here? Before answering that I cannot even answer that yet, no, as well. Let's go back to the first things I told you in this talk, that in this stellar mass range, it could be environment or it could be the AGN feedback. Are we sure that these galaxies do not have AGN? Well, from the studies, we know that in this stellar mass range, usually black holes and nuclear star clusters coexist with each other, with the black hole being less dominant in terms of the stellar mass. We do not have the resolution needed to disentangle these two inside the dwarf galaxies, even in the nearby clusters yet. Hopefully in future we can do that. And the fact that all these galaxies has a nuclear star cluster maybe is suggesting that they have an AGN. We could not find any AGN signatures in the BPT diagram, in the Venn diagram for these galaxies. And in fact, our selection criteria was set there also to make sure that we are not looking at AGN-dominated galaxies. However, we cannot really rule out this possibility because we are looking at the spectra coming from single fiber STSS, and there are also studies suggesting that in this type of data, if the black hole is off-center, you cannot really detect it. So there are some follow-ups with the IFU data for this sample to see if AGN is, if we can see the AGN traces inside these galaxies, and indeed if the AGN is in charge of quenching these galaxies. Okay. Let's also have another look at this plot, and let's only concentrate on the short time scale star formation histories. You can see that these two groups, so short time scale star formation history and long time scale star formation history, are different also in the tau 50. We did several tests in order to classify them, and indeed we saw that from the KS test, they are different in tau 90, they are different in tau 50, they are different in tau 70. So they are different from very beginning in terms of forming of a star formation. And indeed, this plot shows us that if as a galaxy, you are forming your star very rapidly, very fast in the beginning, irrespective of their present day environment, you follow the same star formation history. And this is not the first time that we see this. In the study of Dominguez Gomez or Torres Rios, for a much, much larger sample of galaxies in a more extended stellar mass range and in different larger scale environments, you did see the same. As a galaxy, if you have formed your stars over a short period of time in the beginning, before tau 50, it doesn't matter in what system, in what environment you are anymore. Your fate or your destiny has been set before, regardless of your environment. So what does this mean? For these galaxies, a fast and rapid star formation activity would mean a strong supernova feedbacks, a strong stellar winds that can basically kick out a lot of gas from these galaxies and lead them to total quenching. Some of them have quenched 7.9 gigayears ago. And also, this rapid star formation can lead to formation of NSC nuclear star clusters in these galaxies. For the other group, which have more extended star formation history, this is more puzzling because they are basically showing a similar behavior up to tau 50, but after tau 50, those that now today host a nuclear star cluster are quenched much earlier than those that they don't have a nuclear star cluster. So what does this tell us? Is formation of nuclear star cluster, which is still also an open question for astronomers, that how this is happening. Is formation of nuclear star cluster in charge of quenching galaxies, or is the nuclear star cluster footprint of a quenching mechanism other than environment, could be the AGN feedback, in these galaxies that we are now overlooking? Because most of the time we are looking at dwarf galaxies inside the clusters to understand how environment is affecting them. And this is the trace that is washed away by the harsh environment of the cluster. Okay. So in this study, in this paper, we could not go further. And as I told you, I don't have a good answer, the absolute answer that what had quenched these galaxies given the type of the data that we had and all the limitations that we had. But for this paper and for this talk today, I would like to conclude by putting forward or emphasizing that we have found this rare population of isolated and quenched dwarf galaxies in the most underdense regions of the cosmic web. This is not the complete population. This is a lower limit. With better observations, with Euclid, with Arcis, with JWST, I think we are going to just add to this population. More galaxies of such characteristic will be found. It turns out that all of them have a nuclear star cluster. So do we know all the secrets about formation and presence of nuclear star cluster in dwarf galaxies? Absolutely no, I would say. And also presence of this rare population is bringing us several messages. One is that maybe environment is not as that effective as that we thought for quenching dwarf galaxies. If we are putting too much power to the environment, we are overlooking other possible quenching mechanisms. And that's why we cannot today answer some of the questions, such as why we are finding gas-rich dwarf galaxies in the center of the clusters, or why we are finding completely quenched dwarf galaxies in outer skirts of the clusters. That's because we are only putting all the power to the environment. And I think this should change. This means that maybe we should have a better look at our models. Maybe the supernova feedback that we think only is relevant to low mass galaxies could be also relevant for more massive dwarf galaxies. And this, I think we should also have a better look at that, internal feedbacks in dwarf galaxies. Maybe this means that we don't know much about the environmental voids. Maybe in the voids, we also have the intergalactic medium that is in charge or is capable of quenching the galaxies, some similar thing that is happening inside a small group or inside a cluster. So I think we need to also know more about the environmental voids, environmental filaments, and also maybe my last shot would be that maybe these galaxies have different origins. Maybe they have formed differently from the beginning. That's why they are going through a different evolutionary track. This is an open work. We are still working on this, so we are open to discussions, to follow-ups, to comments about this. If you are interested in this work or you want more details, scanning that QR code should take you to the paper, or I'm here in Granada, and I'm always happy to talk about dwarf galaxies. We can have the discussion. Thank you for your attention.
Thank you very much, Bahar, for this nice talk. I'm open for questions.
Very nice talk. Thank you. Have you checked, or do you have any way to check the metallicity of these nuclear disk structures? I'm asking this because in the Milky Way, for example, the nuclear disk is a region of very rapid evolutions.
Exactly.
So these are normally stars that are old, relatively old, but very metal rich, which means that this is an area that is processing gas very quickly. So that could be linked to the fact that these galaxies stop their star formation earlier than others.
Yeah, that's a very fair point. With the SDSS data, we cannot do it because this is a fiber spectra coming from just one fiber. But certainly that is something that we can do with the IFU data. And that is the first thing that we want to check, the substructures in these galaxies, and if the star formation history is different. And maybe with the SDSS data, we are looking at a particular substructure affecting the light and affecting our results. Yeah.
More question?
Thank you very much for your very nice talk. Very well explained.
Thank you.
Your very thorough work in these complex topics. When you talk about the possible influence of an ATM, you mean about an ongoing ADA, but these we know that they have a duty cycle that depends on, I don't depend on the time scale is,
Yeah.
how it depends on the mass of the platform.
Yeah.
How would it affect if you not see this switch off now, but it was on about 5 million years ago or whatever?
That's a very relevant question. I think with the IFU data and with the stellar population models, seeing the gradients of stellar populations, we can see something. So if I believe that is what I expect, is that if they are quenched by AGN some time ago, then the quenching should happen inside out. So the internal population should be much older than the outer skirts of the galaxy, or we should see the difference in the metallicity of these galaxies. So I think that could be answered using the maps of stellar populations in these galaxies. I'm not sure. I don't know. But that would be one of my approaches to see what's happening there.
I'm going to follow up on that. Have you been able, I might have missed it, have you been able to look at the cell population gradients, or are you planning on doing it?
No, this is SDSS data.
Okay.
But we tried to look at AGN sources on different parts of the wave, on different wavelengths. There's either no observation or no detection for these galaxies. So that's actually one of the other follow-ups, to look for AGN sources in the parts of the wavelength that are more sensitive to these beasts.
Coming back to the metallicity, even with a single trial spectroscopy, you should be able to find differences in the alpha elements.
Yeah.
If the quenching was done at the beginning or later.
Yeah, so from the Pipe 3D, we have an average age and metallicity estimate for these galaxies. In terms of metallicity, they are following the similar mass metallicity relation with a slight tendency to be more metal rich, but the error bars are big, so I cannot drive any robust conclusion on that. For the chemical enrichment, unfortunately, the signal to noise of the SDSS data is not high enough. And usually using the codes, full spectral fitting codes like PPXF, we also have to input the regularization, which also I'm not really confident with playing with the regularization and getting the alpha over Fe. So I think all of this will be solved with deep IFU data, if I manage to convince people to give me the time for that.
Very nice talk. So I'm guessing that with cavity data, you won't be able to do it in like a 10-meter telescope.
Yeah. Yeah, I mean, maybe with LAR we can do something, but as you know, most of the time is allocated to PPAC and for more massive galaxies because they are less expensive for observations and also less complicated in terms of, I would say, data reduction and everything. But we are planning to observe these galaxies with Megara, which will be the central part of the galaxies, and preferentially with Muse, so that we can also have a look at the outer skirts. Maybe they have some signs of interaction. I don't know. In the current data, we didn't see anything, but IFU would really give us the view.
More questions? See you none. Thank you very much again, Bahar.
Thank you.